Good morning everyone, welcome to One Concept Per Day portal. So today's concept is about gravitational potential, and this paper is 2006 May TZ2 science. Okay, now let us begin with this. So define gravitational potential at a point in a gravitational field. What do you mean by gravitational potential? Simple. So this is for 3 marks. So how do you write? The first mark would be something like gravitational potential is nothing but work done per unit mass in bringing, or maybe you can use moving, a small mass from infinity to that point in a gravitational field. So I define this. If you still want to write it an equation, which will always put you some marks, you can write potential V is equal to W divided by M. If it was asked for electrostatic potential, you can write Q. If it is asked for gravitational potential, you write this by M over here, W by M. Okay, work done per unit mass in bringing or moving a small mass from infinity to that point in a gravitational field. This is what we call gravitational potential. Okay, so if you still, you can write this as V final or Vp minus V infinity. You can write, and you can say V infinity is equal to 0, and you can draw a diagram if you want. Okay, it's always better. So you can write. So this is your point P. This is your small mass M. This is your infinity. This is your origin here. You have brought the mass from here to here. That's what we have got here. Okay. In fact, I'm sorry. This will be V infinity. Sorry, Vp minus infinity. Exactly. Vp minus infinity. Right. Next question. A planet has a mass m and gravity and radius r. The magnitude g naught of the gravitational field strength of a planet is given by g naught equal to capital G capital M by r0 square. Okay. Use this expression for deducing that the gravitational potential V naught at the surface of the planet is given by so much. So you need to prove V naught equal to minus G naught into R0. How do we do this? So towards it, what is being known to you? We have known the value of G naught equal to Gm by R square. So we know G0 is equal to Gm divided by R square. This is known to you. Now we also know that V0 is equal to minus Gm by R. Okay, minus Gm by R. So as a result of it, what we can do is we can now do what we will do. We can take from here. We can now write here Gm is equal to minus V0 into R. Okay, from this expression. So now we will take this value of Gm and substitute it over here. When you do this, what do you get? You get this as minus V0 R naught. So R naught over here divided by R naught square. The square and the square R naught goes away. So you get this as minus V0 divided by R0, or V0 is equal to minus V0 R0. So as required, we have proved it. Okay. So only thing is you need to mention. See, if you just write like this, you will not get mark over here. You need to mention that the potential on the surface of the planet is given by V0 equal to minus Gm by R0, where R0 is the radius of the planet. Okay, so you should write this. Okay, so write it down if you want. We know that. You should write. We know that potential V0 at the surface of the planet is, from here you should write this one here. Okay, and then you have to proceed further. Okay, next. The graph shown below shows a variation with distance r from the center of the planet of the gravitational potential V. R of the planet is given as 5 into 10 power 6. Values of V are not shown for r less than r0. Which means what? Values of V versus r, potential versus the distance of an object from the planet is shown over here. And inside the planet, what happens has not been shown. Okay. Now here you see it is 0.51, 1.52 multiplied by 10 power 7 here. And here you see 0, minus 0.5 minus 1 multiplied by 10 power 7 here. What is this now? This potential. And here it is 0.5 over here. Okay. Now The radius of the planet is 5 into 10 power 6. What does it mean? That means I can see this is in 10 power 7. If I write this in terms of 10 power 7, I get this is 0.5 into 10 to the power of 7 over here, right? Meters. So which corresponds to this point. The x coordinate is this. So at this point, that is at this point, now look at the curve. Where does it cross this point? Where does it touch this point? See, for example, if I want to find what is the value of the potential at a point minus 0.5 over here, I can find out what is this value, which is around 4 over here. Okay. Now, if I say what is the value at, sorry, not minus 0.5, at a value equal to 4. 4 at 4 into 10 power 7 meters, what is the potential? You get the answer minus 0.5 into 10 power 7 joules per kg. Okay. Now, if I say, if I look at something like 0 over here, see, as I keep on moving down like this over here, what's happening? So this is my planet. Okay, this is my planet, and then this is my radius r. And when I say this 4 over here, what is this now 4 here? 4 into r, 4 into 10 power 7 meters is what it means. Okay, which means, so what is the radius over here? 0.5. So this value is 0.5 into 10 power 7. When I say 4 over here, that means from this surface, 3.5 into 10 to the power of 7 meters away from here, there's a point P, and if I find out what is the potential at this point, it is seen to be minus 0.5 into 10 power 7. Minus 0.5 into 10 to the power of 7 joules per kg. Okay. The first thing what I have done is, I have interpreted physically the graph along with the problem. That's the question I have made. Okay. Graphically I have interpreted this. Now, so if I say something like at this point, so which is at a distance of 2 into 10 to the power of 7 over here, where in the diagram will it correspond to? So this would correspond to a 0.7 over here. Okay, so this would be 2 into 10 to the power of 7 over here, and as a result of it, the potential at this point would be minus 1 into 10 to the power of plus 7 over here, right? So this is how you need to interpret first. You need to understand what is the graph being given, and then you go further. Okay, now V versus R has been given. Now what is being asked? What is that I need to show? Use the graph to determine the magnitude of the gravitational field strength at the surface of the planet. You need to find out what is the magnitude of the gravitational field strength. He is asking you to find out gravitational field strength. Remember, it is field and not potential. Okay, so what is given here is potential. You need to find out the field. Now what do we do? So what is the relationship connecting potential and field? We are already seen here. What is that relationship? It's already given here as potential is equal to field multiplied by the radius, right? So therefore, let me write it down once again. I will write potential, which you get it from the graph, okay, is equal to field multiplied by radius. That's what I have. Now towards it, or radius, or maybe you can write distance, distance. Okay. Incidentally, the distance is nothing but the radius of the sphere over there. Now, what is the radius? We already know, because he is, why radius should I take? I should take radius because he says at the surface of the planet. The radius is nothing but 0.5 into 10 to the power of 7. This multiplied by field. What is the field at that point? Which I do not know. Let me write G0 here. Okay, and what is the potential at this point? Which I can find from the graph. At 0.5 into 10 power 7, 0.5 into 10 power 7. If I draw a line vertically, this will intersect the curve somewhere at this point, which comes out to be around this 3.5, this should be 3.9 over here. The point which I have written is 3.9. So therefore, I will write this as 3.9. So I will write this as 3.9 multiplied by 10 power 7 is equal to so much. There is a negative over here. Minus 3.9 10 power 7 is equal to so much. So G0 should be equal to minus 3.9 into 10 power 7 divided by 0.5 into 10 to the power of 7. So this goes away. So you get this as 3.9 multiplied by 1 by 0.5 is 2, which would be 2 9s are 18, 1, 2, 3 is 6, 7.8 meter per second square. Put a negative sign here. Okay, that's the gravitational field strength is seen to be 7.8 meter per second square, the magnitude. Okay, because he's asking you only the magnitude, so I will just write magnitude of G0 is equal to 7.8 meter per second square. Okay, question number D. A satellite of mass m is launched on the surface of the planet. Use the graph to estimate the minimum launch speed. You need to find out the velocity of the satellite that you are going to launch in order to reach a height of 2 into 10 power 7 meter. Let us visualize it first. So this is the planet, and this was the place where the satellite is present. You gave a push, which means you are giving an energy here. When you give an energy, the rocket, when the satellite went all the way along to this height. The height was h, was so much over here. This is the height. H is given to you, and you need to find what is the speed with which you launch this rocket. That's the question. With what speed did you launch the rocket? So how do you do this? So you can use your work energy theorem. How do you use work energy theorem? Find out what is the kinetic energy here. Kinetic energy Ke1 here. What is the kinetic energy 2? Kinetic energy 2 here. What is work energy theorem first? Work energy theorem tells you changes in kinetic energy is equal to changes in potential energy, which is equal to work done. That's the formula. So therefore, changes in kinetic energy would be Ke1 minus Ke2 or Ke2 minus Ke1. Anything can be. Okay. I'll just take the magnitudes because I need a velocity, right? Whenever velocity I have, which means the velocity should be positive for me. Because if one side becomes negative, I definitely need to take the magnitude. The square root of velocity will be imaginary. Why do I say all this? Because when I do kinetic energy, I get this as half mv square, and I need to take the square root of v. When I take the square root of v, whatever you have here should be positive. Okay, so I'm just taking this as positive value. This should now be equal to delta P. What is delta P? The potential energy at this point, Pe1, and the potential energy at this point, it is Pe2. I need to take the difference between these two. Now, how do I get the difference? Now, Pe2 minus Pe1, I'll write it down. Pe2 minus Pe1. Now, how do I get this Pe2, Pe1 here? So, because if M is known to me, M is already given to me, I can just find out from here, right? So, I can get this Pe2 and Pe1 from the graph. That's what has been asked. So, how do I get it? So, potential energy. Let me go back to the graph. Now, at a height of 2 into 10 power 7, what is the potential energy? Let us find out here. At a height of 2 into 10 power 7, the potential energy is somewhere over here. 10 power 7, it is somewhere over here, which is going to be minus 1. See, somewhere over here. It's going to be minus 1 into 10 power 7. Okay, let me write down. So, at this point, the potential energy is minus 1 into 10 to the power of 7. And at this point, what is this? 0.5 into 10 power 7. At the radius point. At the radius point, what was it we got? We already got this value. This was going to be around 3.9, right? So how do I know? I have already found out here. Where is it? We have taken here, right? Potential at this point is equal to minus 3.9 into 10 power 7. I write that also here. I write this as minus 3.9 into 10 power 7. Okay, we have got this. Now take the difference between these two. If I take it, what should I get? I should get this as 2.9 into 10 power 7. Okay. Now what is this now? This is not potential energy. This is only the potential. Now if I want potential energy, what should I do? I should multiply this by the mass of the satellite, right? Because m delta v, okay, is nothing but the work done or potential energy. So therefore you have half mv square is equal to m into so much. This m and m cancels. I need not use this value of the mass of the satellite. I don't need this, right? I just need the value of this one. So what I will do is I'll write v square is equal to 2.9 into 2 into 10 to the power of 7, which should now be 2 9s are 18, 1, 2 2s are 4, 5.8 into 10 to the power of 7, this is nearly 58 into 10 to the power of 6. So I can write v is equal to square root of 58 into 10 to the power of 6, which should now be, let us take square root of 58, should now be 7.61. 7.6 into 10 power 6 square root should be 10 cube meter per second. Thus, the velocity of launch should be around 7,600 meter per second, or 7.6 kilometer per second. 7.6 kilometer per second. This is the speed at which you should launch the satellite so that it reaches to that height. Which height? The height of 2.2 into 10 power 7 meters. Okay. Let us go to the next one. Right, I think this is the next question that we have. We'll stop here for this question, and I will continue with the next question in the next video. Okay, because it's a bit longer. We'll stop. Thank you.